In this video, we're going to work through the last few examples from our application handout. So this is the 8th one. It says we got this function and it models the amount of potassium remaining t billion years later from an initial sample of a sub 0. Now notice that t billion years, that means potassium is very, very stable. It's not going to decay very rapidly whatsoever. We're being asked if there's initially 120 grams or 8,000 grams, how long will it take for the sample to decay until half its size? What we're going to see is that it's actually independent of how much you start with. Alright, so what we're going to do is plug in the initial amount right away to the model. A sub 0 is 120, put that number in. How long will it take to get to half? Well, half of our initial amount, 120, would be 60 grams. So we're going to put in 60 for A and then solve for T like we've been doing. So we put that in there, and we want to isolate the factor that involves the T by dividing by 120, and that leaves us with 1/2 equals e to the negative 0.52912 t. And then we're going to convert this from exponential to logarithmic form. Remember, log base e is natural log. And then we're going to eventually solve for t by dividing by negative 0.52912. And so we get that t is the natural log of 1/2 over negative 0.52912. And that's about 1.30999 billion years. Here we have the exact form. Here we have our decimal approximate. And that's the same process you would take to solve it if there was initially 8,000 grams. You'd set a sub 0 to be 8,000, set it equal to, in this case, half, which would be 4,000, but then you would end up solving the same exact equation. So it gives us the same answer, so we don't even need to do part B. Number 9, number 10 is similar to that. We'll just do number 9, and we're going to do this in two ways. One is going to be using this model, a sub 0 times b to the tth power. We're going to actually find the base here, given the information that the half-life of silicon 32 is 710 years. So we're going to put in the initial amount. We've got 200 grams to start with. We're told after 710 years, half as much is going to be left, which means we're only going to have 100 grams remaining after 710 years. So plug in 710 for T, plug in 100 for A, and then we're going to try to solve this time not for T, but for the base B. Divide both sides by 200, and then simplify, and we get that b to the 710th power, 710 power, is equal 1/2. Now, just like taking square roots, we raise both sides to the 1/2 power. Here we're going to raise both sides to the 1 over 710th power, which is like equivalent to taking the 710th root. Now, we only want the positive solution of that because b, our base, we want to be a positive number. All right, now put that back into our formula, and then we simplify by multiplying the exponents together, and we get that the amount left after t years will be 200 times 1/2 raised to the t over 710 power. Now, that formula makes pretty decent sense. We're supposed to be getting half as much after 710 years. So every multiple of 710 years, you're going to multiply by another factor of 1/2. Now, from this point forward, it's easy to answer the question. That's the hard part, is determining the base, which tells us how this silicon 32 decays. To find out how much will be present in 600 years, we just need to plug in 600 for T. Doing that, we get approximately 111.336727 grams. Got the exact formula, exact amount, and the decimal approximate. Now we're going to redo this by using the second formula. That is, we can always model something that's growing or decaying exponentially with base e. Alright, so this time we're going to use the model a sub 0 times e to the kt. We're not going to see that this is going to be that much simpler. We still have to go through the same process. We know the initial amount's 200 grams. We know the half-life is 710. So this time we're going to put 710 in for T and put 100 in for A, the amount left. This time we've got to find the decay rate, which shows up in the exponent. This is the continuous decay rate. So divide by 200, simplify to get e raised to the 710 times k power equals 1/2. Now we're going to convert from exponential to logarithmic form and then solve for k, not t. So we get that k is equal to, by dividing by 710, the natural log of 1/2 over 710. So now we're going to take this value and plug it in for k in our model. And then we'll be able to determine t, or determine the amount left. So plugging that in for k, it leaves us with a kind of complicated looking formula. Now all we need to do though is to plug in 600 years and determine the amount left. So plug in t equals 600, and we end up taking a calculator, computing it, and we get the same exact answer, of course, using this model as we would before. They are equivalent to one another. And that's the end of that problem. The last question on the sheet, number 10, is very similar to this one. The solution's identical, just different numbers.